So let's say that we want to convert from moles to things, moles to any physical object, like you said, atoms or molecules or ions, formula units or something we'll talk about later. So let's take a look at how we do that. First question might say, how many molecules are in 3.1 moles of water? We want to start off with the number we're given. So we have 3.1 moles of H2O, just like this. Now, in order to do this, we're going to want to set up our tables just like we did with our unit conversions. Because what we can do is we can say how many molecules. And so we know we want to cancel moles of H2O. So that has to be on bottom. But we want to go to molecules. And unfortunately, molecules doesn't have molecules. H2O doesn't have an abbreviation. So we have molecules H2O. The question is, what is the conversion factor here? How many molecules are in a mole? Well, we said that mole by definition is just a number. It's a number of certain things. What number is it? 6.022 times 10 to the 23rd. So that means we can say 6.022 times 10 to the 23rd molecules are in 1 mole of water. At this point, let's cancel the units that cancel. Moles H2O cancels, moles H2O cancels. We just have molecules of water left. And so at this point, you can get out your calculator and you can say multiply across the top. So 3.1 times 6.022 times 10 to the 23rd, and then divided by 1. And when you do that, we end up getting an answer of 1.8. Actually, in this case, it's actually not going to be 1.8. It'll actually be 1.9, because to make sure significant figures, we have 2 significant figures sitting over there. So we'd say 1.9 times 10 to the 24th molecules. Like that. And so that would be the answer that we're going to get here. So we end up with 1.9 times 10 to the 24th molecules. That's how you're going to set up one of these. If we had to do this in reverse, we'd say 7.37 times 10 to the 25th atoms of sodium make up how many moles? And so we'll start off 7.37 times 10 to the 25th power atoms of sodium. Symbol is just Na. That's how we're going to start off our table. We want to cancel atom sodium. That didn't look like an N at all. So atoms, I cannot write today. So atom sodium, like this. We want to go from atom sodiums to how many moles. So we're going to have mole sodium on top. The question is, how many atoms in a mole, or how many moles in an atom? An atom is a thing. And so in 1 mole, there are going to be 6.022 times 10 to the 23rd. So 6.022 times 10 to the 23rd atoms in 1 mole. Look at our units. Atoms of sodium is going to cancel off. The only thing that we have left is just moles of sodium, which is what we want. So we can get out our calculators again. 7.37 times 10 to the 25th. So we say 7.37 times 10 to the 25th power times 1 divided by 6.022 times 10 to the 23rd. And so putting that in the calculator, you end up with a final value of, I get 122. So this has 1, 2, 3 significant figures, and so our final answer is going to be 122 moles of sodium. So 122 moles sodium tells us exactly how many moles there are in 7.37 times 10 to the 25th atoms. So that's how you'd work out any types of conversions from moles to things, moles to some sort of object like an atom or something like that. So continuing here, what if we wanted to instead convert from moles to grams? So to do that, basically what we want to do is that the conversion between moles and grams is going to be the atomic mass, or if it's a molecule, the molecular mass that you get off your periodic table. And so we start off in a very similar way. We start off with the number we're given. So in this first problem we have 5.3 moles of iron has what mass? And so we're going to say 5.3 moles of iron, Fe. Set this table up right here. And then we want to get rid of moles Fe. We're looking for mass. That's going to be in grams. So we put grams Fe up here. And when I'm doing this, just as I want you to note, I am including the substance here, moles iron, grams iron, moles iron. Right now, for what we're doing, that's probably not necessary, but we're going to get to things later in the year where you have to include those. So it's probably a good idea to make a habit of writing those in. But for right now, they're technically not needed, but just sort of be aware of that, so you may want to get used to it. So we've got grams iron, we have moles iron. Well, we're looking for the number of grams there are in a mole. And for any substance, we said for carbon-12 that there were a mole of carbon-12 atoms in 12 grams. We said that for hydrogen that there were 1.01 grams in 1 mole. And so, as we said before, that means the atomic mass is going to be the number of grams in 1 mole. So we have 1 mole right here. We look on the periodic table and it tells us that iron has a mass of 55.85 grams per mole. So 55.85, 85 or 86? 85, I don't know why I wrote a 6 there. So 55.85 grams of iron in 1 mole iron. Units, moles iron cancels off. That gives me only grams iron left. And so once again, let's plug it into the calculator. Multiply across the top. 5.3 times 55.85 divided by 1. And so we end up in this case with an answer of 296. Since we only have 2 significant figures here, that's actually going to round to 300. And so we have 300 grams of iron. And so that's going to be our final answer here. Or if you wanted to, you could do 3.0 times 10 to the second grams of iron. Both of those are correct. The second one conserves the right number of significant figures, though. So either one will be fine. So this is how you'd go about figuring out conversion from moles to grams. Now let's do the opposite. Find the number of moles in 190 grams of CO2, carbon dioxide. So in this case, we start off with 190 grams of CO2, just like that. So we're going to set this up. We want to get rid of grams CO2. We want to cancel it so it gets on the bottom. We're looking for moles. So we have mole CO2 on top. We said anytime you convert between grams and moles, you want to use a mass. You want to use an atomic or molecular mass. CO2 is a molecule, so we're going to have to figure out what the molecular mass of CO2 is. Well, sort of setting this up, we know that that carbon, we have 1 carbon, so we have 1 of those. And oxygens, we have 2 of those. Carbon has a mass of 12.01. Oxygen has a mass of 16. So if we add those 2 guys up, we'd say 1 times 12 is obviously just 12, so 12.01 plus the mass of the oxygen, 2 times 16, that's 32. And so when doing this, we end up with 44.01. So that's going to be the mass in grams per mole of carbon dioxide. So we put in 40, whoops, that's not the right spot. Not moles per gram, it's grams per mole. And so this is how we're going to sort of set that up. So 1 mole is 44.01 grams. That is something you need to watch out for. There is a tendency sometimes to put things in the wrong spots. Just look at the units. It's 44.01 grams per mole. That means it goes with the grams, not with the moles. Alright, so continuing here, we can once again multiply across the top, divide by the bottom. So we have 190 times 1 divided by 44.01. And so doing that, we get 4.3172. Significant figure-wise, we have 1, 2 here, and so our answer will just be 4.3. So there are 4.3 moles of CO2 in 190 grams of CO2. And so that's how we go from moles to grams. All right, so continuing here, what if, instead of doing as we have in these last two, what if we had to convert from grams to things? We've done things to moles and we've done grams to moles, but if we have to do grams to things, how do we do that? Well, general process is going to look something like this. If I have, say, things here, and I have grams here, then the basic thing you're going to use to go between it is, of course, going to be moles. You can go from things to moles, and moles then to grams. Or, if you had to go the other way, you go from grams to moles, and then from moles to things. And so this is the process we're going to do here. Moles is sort of our grand central station here that lets us go between most anything, and we're going to find that out the whole year. It's sort of the nice special thing that we always want to go to. First step is on pretty much any conversion we're going to do is going to usually end up being convert to moles, because moles lets us go between different things. It's like our super universal translator that lets us convert from anything to anything else. So first thing, always convert to moles first. And so if our question is how many cobalt atoms are in 14.2 grams of cobalt, then we start off with the number we're given, 14.2 grams of cobalt. Set up our table. We want to cancel grams cobalt. Then we want to go to what first? We want to go to moles first. So we put moles cobalt on top. At this point we say grams to moles. What do you use to convert between those two? A gram is a unit. It's grams. We're going to use the periodic table to look up the atomic mass of cobalt. And doing that we see it's 58.93 grams per mole. So 58.93 grams in 1 mole of cobalt. That gets that. At that point, we have now canceled out grams of cobalt. We're in moles of cobalt. And if we have moles of cobalt, that means we can go ahead to atoms, which is what we're asked about. So let's continue this setup here. We have moles cobalt on bottom. We have atoms cobalt on top. We say how many atoms are in a mole? Well, in 1 mole there are 6.022 times 10 to the 23rd power. And so at this point, now all we have to do is just solve the problem, because our moles of cobalt have been canceled. The only thing we have left now are atoms of cobalt, which is what we asked for. So setting this up, we'd say 14.2 times 1 times 6.022 times 10 to the 23rd divided by 58.93 divided by 1. And so doing that, I end up with 1.45108 times 10 to the 23rd. Since our original value had only 3 significant figures, then this one will too. So 1.45 times 10 to the 23rd atoms cobalt. And so that is going to be our final answer, 1.45 times 10 to the 23rd. So that's how you'd set that up. Our next one here, sort of the reverse way, we have 1.25 times 10 to the 23rd molecules of UF6. That's uranium hexafluoride. UF6 would have what mass? And so we start off 1.25 times 10 to the 23rd molecules of UF6, and we're going to set that up. We want to convert from molecules UF6, and we want to go into what first? Well, always go to, once again, moles first. So moles UF6. And so to do this, we say a molecule, is it a gram or is it a thing? A molecule is a thing. It's a physical object. And so because of that we know that there are in 1 mole of UF6, there are 6.022 times 10 to the 23rd power molecules of UF6. Continue along here. We want to then go from moles UF6 into, or we want our final one, which is mass, that's going to be grams. So grams UF6. And so now we have to figure out, well, what's the mass of UF6? Well, this has 1 uranium. So we'd say 1 times the mass of uranium. Uranium, looking this up, is 238.03. And we're going to add that to how many fluorines do we have? We have 6. So 6 times the mass of fluorine, which is 18.998. That just rounds to 19. And so you can go ahead and take the calculator and say 1 times 238.03. And so 238.03 plus 6 times 19. And so when you do that, you end up with a mass of 352.03. And that is going to be the molecular mass of uranium hexafluoride, UF6. So we say 352.03 grams UF6 in 1 mole. And so at this point, units, we've got molecules UF6 cancels with molecules UF6. Moles UF6 cancel with moles UF6. We've only got grams UF6 left. And so, so to do this, we'll start off 1.25 times 10 to the 23rd, so what's on top, times what's next on top, which is 1, times 352.03, and then divided by 6.022 times 10 to the 23rd, and divided by 1. Doing so gets us an answer of 73.07. Since we had 3 significant figures to start, we're going to have 3 significant figures for our answer, and so that means we'll have 73.1 grams of UF6, and that's going to be our final answer. And so that's how you go about converting from molecules to grams, or in general from any type of thing to a gram.
One last topic that we want to look at here, and that's dealing with cases where we want to use the moles of one substance, a substance has been given, to determine the moles of a different substance. Best off just to explain this by using an example. Suppose we had a question like this one that's right here. How many moles of oxygen are in 2.3 moles of CO2, carbon dioxide? So we're given the amount of the carbon dioxide. We have 2.3 moles of carbon dioxide, but we're asked about the number of moles of oxygen. So we've changed substances. We've gone from CO2 to oxygen. Now, in order to do this, to make this conversion, what we're going to have to do is we're going to have to use something that's called mole ratio. So mole ratio is a way of looking at the number of each element that's in the molecule. So in this case we have CO2, and so this is one that we've sort of looked at before. So CO2 we know is going to have, it has an implied 1 that's right there for the carbon, and so that means that we have 1 carbon and we have 2 oxygens in this. And technically what we're saying here is that there's 1 carbon and 2 oxygens for every 1 CO2. Now that's a ratio, because if we wanted to find the ratio of carbon to CO2, well, that would be 1 carbon to 1 CO2. It's a 1-to-1 ratio between those two from an atom perspective or a mole perspective. The same thing if we wanted to find the ratio of oxygen to CO2. We'd say that there are 2 oxygens for every 1 carbon dioxide molecule. And so if we were looking at our oxygen to CO2 ratio, that would be a 2-to-1 ratio. Now, once we know that ratio, that's a ratio of the number of oxygen atoms to the number of carbon dioxide molecules. And because of the fact that there's the same number of oxygen atoms in a mole as there are carbon dioxide molecules in a mole, 6.022 times 10 to the 23rd, we know that there will also be a ratio of moles that's the same way. So there'll be 2 moles of oxygen for every 1 mole of CO2. Or if we're looking at carbon, there would be 1 mole of carbon for every 1 mole of carbon dioxide. So let's do some examples on this. Let's look at some of the mole ratios that we have for 2 different examples, 2 different substances. So our first one that we have right down here, C12H22O11. And so let's say that what we want to figure out is we want to figure out what's the mole ratio of carbon to this molecule right here. And so we'd say, okay, we've got 1 molecule of C12H22O11. How many carbons do we have for each molecule? Well, there are 12 carbons in here, so we have 12 carbons for every 1 C12H22 O11 right there. And so that means this is going to be a 12-to-1 ratio of C to C12H22O11. Now, in terms of actually using this in a problem, what we do is we'd say, all right, let's start off with an amount that we're given. So if we were told that we had, let's say, 5 moles of C12H22O11, we'd start off by simply saying, okay, 5 moles of C12H22O11, and we'd set up our table, and just as before, we'd want to get rid of moles of our C12H22O11, so C12H22O11, and we want to go to moles of what we want. In this case, we're saying carbon. So how many moles carbon are there for every mole of C12H22O11? That's how we set up our mole ratio. We go from moles of what we started with, which is this guy right here, to moles of what we want, which we've said is going to be that carbon. So we put moles C12H22O11 on the bottom, we put moles C on top. The mole ratio between these two is for every 1 mole C12H22O11, 1 mole of that molecule, there are 12 moles C. And so now we can figure out the number of moles of carbon. We just multiply across the top, so 5 times 12 divided by 1, because that's going to cancel right down there, leaving us with 60. And so if we had 5 moles of C12H22O11, we'd have 60 moles of carbon, which then we can convert into grams of carbon or convert into carbon atoms the same way that we've done before. So let's try another one. Let's look at PO3. So for PO3, let's go ahead and figure out what would be the mole ratio of both phosphorus and oxygen. So if I was trying to convert from, let's say that I had 6 moles of phosphorus right here, and I want to figure out how many moles of PO3 I have, then I would first say, well, I want to get rid of my moles of phosphorus. I want to go to my moles of PO3. And now I've got to figure out what's the mole ratio, because I'm changing substances. Well, for every molecule of PO3, there are how many P atoms, how many phosphorus atoms? Well, there is 1 phosphorus atom in this molecule. So in 1 mole of PO3, there is 1 mole of phosphorus. And then at this point, that cancels out moles of phosphorus. I can multiply across the top. 6 times 1 divided by the bottom is 1. Tells me that I have 6 moles of PO3 in here. That's a 1-to-1 ratio because there's only 1 phosphorus in this particular molecule. Now, if, on the other hand, we'd had oxygen, if we'd said this starts with 6 moles of oxygen, we do it the same way. We still want to get rid of that original moles of oxygen. We want to go to moles of what we want, which in this case is PO3. But in this case, the mole ratio won't be 1-to-1 because there isn't 1 oxygen in 1 molecule of PO3, 1 oxygen atom. There are 3. Because there are 3 oxygens in every 1 PO3. And so for every 1 PO3, there are 3 moles of oxygen. And now we can go ahead and do our conversion. Cancel moles oxygen, gives us moles of PO3, which is what we want. 6 times 1 divided by 3 gives us a total of 2. And so we would have 2 moles of PO3, because that's what's remaining here. So PO3 is our value we have there. So that's how you go out working out a problem with a mole conversion. So another example we could have here would be a case where we have to convert moles from one substance to a different substance. So our example here, how many hydrogen atoms are in 11 moles of NH3? All right, so we always start off with the amount we're given. So we're given 11 moles of NH3, which is ammonia, is the name of that substance. So we've got moles NH3. We're looking for atoms, that's what we're trying to get to, but we're not looking for atoms of NH3, it would be molecules anyway. We're looking for hydrogen atoms. So because of the fact that we started off with NH3 ammonia, we're going to end with hydrogen, we're going to have to switch substances. And when you switch substances, you're going to need to use a mole ratio. And so we're going to go from moles that we start with. So moles of NH3 to moles of hydrogen will be our steps here. So we're going to cancel moles of NH3 of ammonia. We want to go to moles of what we want, which is that hydrogen right there. And now we've got to find the mole ratio. So to find the mole ratio, we want to look at the molecule. The molecule is NH3. And then we ask, well, what atom are we interested in? We're interested in hydrogen. So how many hydrogens are in 1 molecule of NH3? Well, it's 3 because there are 3 H's right here. So we'd say 3 moles H for every 1 mole NH3 because there are 3 hydrogens in every 1 ammonia molecule. Once we've got that, then we can go ahead and do our next cancel on this because that's going to cancel moles of NH3. Now we've got moles of H. But the question was not how many moles of H, it was how many atoms of H. So we're going to have to continue on here, and so once we have moles, we can go on to whatever substance we're looking for. In this case, it's atoms, so it's things. So we're going to say moles of H to cancel that out on bottom. We'll say atoms, H on top. And so at this point, how many atoms are in a mole? Well, in 1 mole, there are 6.022 times 10 to the 23rd Avogadro's number of atoms. And so when we do that, that's going to cancel out moles of hydrogen. That's going to result in atoms of hydrogen, which is what we're looking for. And now it's just a matter of doing the math, multiply across the top, divide by the bottom. So we'd say 11 times 3 times 6.022 times 10 to the 23rd, divided by 1. So we get an unrounded value of 1.98726 times 10 to the 25th atoms, if I can fit it in here, of hydrogen. Significant figure-wise, we started off with 11 moles. That's got 2 sig figs, so we're going to round this to 2 sig figs. 1.98, that means these two are our 2 sig figs here. 8 is going to make the 9 round up, and that's going to make the 1 round up. So we end up with just 2.0. So 2.0 times 10 to the 25th atoms of hydrogen would be our final answer, correctly rounded. All right, so let's try another one. What mass of carbon is found in 22 grams of CO2? So in this case, we know that our first step is going to be to say, all right, we start off with 22 grams of carbon dioxide of CO2. We want to always go to moles first, and so we're going to say, all right, 22 grams of CO2. We want to cancel grams of CO2. We want to go to moles of CO2. So to find these values, we want to find what is the molecular mass of carbon dioxide. So carbon dioxide has 1 carbon. So we have carbon, we have oxygen. So there are, let's see, so 1 carbon and 2 oxygens. Carbon has a mass, if you look on the periodic table, of 12.01 grams per mole. Oxygen has a mass of 16.00 grams per mole. And so that means that the carbon will be 12.01. The oxygen is going to be 32.00. Add those two up. We get a 0, 1, 4, looks like 44.01. And so that will be the molar mass, so 44.01 moles of CO2 in 1, oops, that's entirely backwards. Got to flip that around. I apparently can't read straight, so get rid of that. Hopefully you caught that as we were doing that. Because that's not the number of moles in 1 gram. It's the number of grams in 1 mole. 44.01 grams per mole, not moles per gram. So that should be 44.01 grams in 1 mole of CO2. Now at this point, that should cancel out our grams of CO2. Now we have moles of CO2. Well, what do we want to go to next? Normally we go from moles of our substance to what we're looking for, but in this case we're switching substances. We start off with CO2, but the question is what mass of carbon? Carbon and CO2 are not the same substance, so we're going to have to use a mole ratio to convert from CO2 to carbon. And so to do that, we want to once again cancel out our moles. So we're going to put moles of CO2 on the bottom. We're going to put moles of what we want, which in this case is carbon. Moles of carbon on top. So we want to find the mole ratio. So to find the mole ratio, we say how many atoms of carbon are in 1 molecule of CO2? Because CO2 is the molecule, so we know it's going to have the 1. And in this case, we say how many carbons are in CO2? Well, we already answered that. Right over here. 1 carbon in there. So it's going to be a 1-to-1 mole ratio. So that's going to make things a little easier here. So once we've got that, that lets us cancel out our moles of CO2, gives us moles of carbon. Now the question asks not how many moles of carbon, but it asks what mass of carbon. So we want to get rid of our moles of carbon, cancel that out, go to grams of carbon. And so here we're going to use the molecular or the atomic mass of carbon. And so the atomic mass of carbon, look on the periodic table, we already saw it before, 12.01. And so they're 12.01 grams in 1 mole. And so once we've got that, that's going to cancel out moles of carbon. The only unit left is grams of carbon, and so mass is grams, so that gives us grams of carbon. That's what we're looking for. And so we should be able to go ahead and solve this out. Multiply across the top, divide by the bottom. And so in doing that, we have 22 times 1 times 1 times 12.01 divided by 44.01 divided by 1 divided by 1. So I get 6.0036. So 6.0036355 unrounded grams of carbon, but we want to round to the correct number of significant figures. And so sig fig wise, we had 22 grams. Whoops, wrong one there. So we had 22 grams of carbon, and so that's 2 sig figs. So we're going to round this to 2 sig figs, which since that 0 is going to leave that 0 down, this will just end up being 6.0 grams of carbon is our final answer. So they're exactly, or almost exactly, round to the nearest 10th place. 6 grams of carbon in 22 grams of carbon dioxide.